All right, so today kicks off day 10 of my journey to learning cybersecurity using TryHackMe.com resource to give me a structured path. And today we're doing network essentials. Start out with the introduction. If you ever wonder how your computer can dynamically configure its network settings? Have you ever wanted to know how many devices and countries your packets pass through before reaching your destination? Are you curious how all of your devices can access the internet even though your ISP gives you a single address? I don't know the answers. This is perfect. Let's make sure this is right one. And I love this platform. It is pretty easy to navigate, and so far it's given a very structured path. As with anything, I would recommend to make sure that you're supplementing your efforts in learning and you're not just relying on one source. So what I basically mean by that is reinforce what you've already attempted to learn. That way it sticks and you get a very good understanding of it. Because if you just do the bare minimum, just do the classwork or just do whatever, then chances are you're not going to retain the information as thoroughly as you would had you spent a little bit of time outside of the classroom learning whatever concept, reinforcing the learning of any concept or thought or whatever it is that you're doing. So we'll make sure that we get a little bit of time in doing that as well. Man, I'm struggling identifying my path today. Man. Let's see if we can get there real quick. Networking concepts. Okay, networking essentials. All right, this is where we were. All right, to access the materials, start the machine and answer the questions, you need to join the room. Introduction. Looks like I need to join the room. We'll give that a moment to kick off. So this is day 10 of me documenting my journey to learning cybersecurity. Make sure my browser is working properly. This thing is acting up on me. Oh, signed out. Let's get signed in. Okay, so there's no room with this one. The benefit from this room is we recommend, the following the OSI model, ISO and OSI model layers. We learned about that last time. TCP IP modeling layers, Ethernet IP, and TCP protocols, in other words. Starting this room after networking concept is the recommended approach. So cool. Our objective is to understand DHCP, address resolution protocol, ARP, network address translation, NAT, and internet control protocol, which is a ping and a trace route. So that's what we'll get at the end. So get your notepad ready, which we have here, and let's get going. So the first section or task is DHCP, give me my network settings. See what this thing is talking about. Move some stuff around here. Give me just a second. Hope everyone's doing well out there. Appreciate you stopping by. We are learning cybersecurity using TryHackMe.com. And we are taking advantage of the resources available. And we're going to go through the learning modules, talk about those, and do some supplement learning outside of this. We won't just rely on this to teach us. We'll reinforce what we learn as well. So jump in and join the journey. All right, so first task, DHCP, give me my network settings. You went to your favorite coffee shop, grabbed your favorite hot drink, and opened your laptop. Your laptop connected to the shop's Wi-Fi, and automatically configure the network so you can now work on a new TryHackMe room. You didn't type a single IP address yet, your device is all set up. Let's see how this happened. Whenever we want to access a network, at the very least, we need to configure the following: our IP address along with the subnet mask, yep, router or gateway, and finally the DNS server. Whenever we connect our device to a network, the above configurations must be set according to the new network. Manually configuring these settings is a good option, especially for servers. Servers are not expected to switch networks. You don't carry your domain controller and connect it to a coffee shop Wi-Fi. Moreover, other devices need to connect to the server and expect to find the specific IP address. Let's run through that one more time. Whenever we connect our device to a network, the above configurations must be set according to the network manually. Got it. Manually configuring these settings is a good option, especially for servers. Servers are not expected to switch networks. You don't carry your domain controller and connect it to the coffee shop Wi-Fi. Moreover, other devices need to connect to servers and expect to find them at a specific IP address. Okay. Having an automated way to configure your connected device has many advantages. First, it will save us from manually configuring the network. Extremely important, especially for mobile devices. Secondly, it saves us from address conflicts when two devices are configured with the same IP address. Yep. An IP address conflict will prevent the involved host from using the network resource. This applies to local restaurants, Internet Solutions, DHCP. DHCP is an application level protocol that relies on UDP service. Okay. So some very basic introduction into networking, how devices connect to a network and the internet in general. The dynamic host configuration is an application level protocol that relies on UDP. The server listens on the UDP port 67 and the client sends UDP ports to your smartphone or laptop. So let's grab some notes from this. We got some pretty good stuff going on. Access a network. We need the following: IP address along with submask, a router or gateway, and then finally we'll need the DNS server. Whenever we want to connect our device to a new network, the above configurations must be set according to the new network. Manually configuring is a good option, especially for servers. Servers are not expected to switch networks. You don't carry your domain controller and connect it to a coffee shop Wi-Fi. Moreover, only devices needed to connect the servers are expected to find the specific IP address. So basically what this is saying is that the servers should be manually configured. You don't want that configuration to be set dynamically or open, and you only give your server information out to devices that you want to connect to your network. So that makes total sense. Having an automated way to configure a connected device has many advantages. First, it will save us from manually configuring the network. This is extremely important, especially for mobile devices. Secondly, it saves us from address conflicts. When two devices are configured with the same address, the IP address conflict will prevent the involved host from using network resources. This applies to local resources and the internet. The solution lies in dynamic host configuration. Let's write that down. That seems like a good one. DHCP. And this is going to be dynamic host configuration protocol. I love how everything has a protocol. So regardless to where you may sit, certain things should be structured a certain way. You knew that it exists, but it's just refreshing to kind of read and see about it as you go along this journey, if you will. It's an application level protocol that relies on UDP. I would say application protocol that relies on UDP. The server listens on UDP port 70, listens on port 67, and the client sends from UDP, port 68. Your smartphones and laptops are configured to use DHCP by default. Yep. DHCP follows 4 steps: discover, offer, request, and acknowledge. DORA, like the acronym. DHCP, 4 steps. 4 steps. Discover, offer, request, acknowledge. LEDGE, DORA. DORA. And DHCP discover. DHCP discover. The client broadcasts a DHCP discover message seeking the local DHCP server if one exists. Client broadcast a DHCP discover message seeking the local DHCP server. DHCP server if one exists. Makes sense. So initially starts out by seeking the server, wanting to identify if one actually exists. Then there's an offer that takes place, and that is the DHCP offer. The server responds with a DHCP offer, message with an IP address available for the client to accept. Makes sense. So it presents an offer that'll be ready for the client to accept once it's discovered. Makes sense. Then you have the request, DHCP request. The client responds with the request message to indicate that the offer is accepted. The client responds with the HCP request message to indicate that it has been accepted. The offered IP. Makes sense. And then finally you have the acknowledge, and this is where the server responds with a DHCP PAC message to confirm that the offered address is now assigned to the client. DHCP acknowledge. The server responds with DHC PAC message to confirm that the offered IP address is now assigned to the client. Got it. Okay. So that is DORA, the 4-step process, starting with discover. The client broadcasts a DHCP discover message seeking a local IP DHCP server if one exists. So I'm going to put the request out there to discover if one exists. The offer is the step where the server responds back with the offer message with the IP address available for the client to accept. So, hey, I've acknowledged that you're here. Here's the IP address. The DHCP request, the client responds with the DHCP request message to indicate that it has accepted the offered IP. Hey, we acknowledge that we accept this, the offered IP. Thank you so much. We're glad to take this pass. And then you have the acknowledge step, which is the server responds with a DHCP PAC message to confirm that the offered IP is now assigned to the client. And that's just the final step in the process that everything's accepted. And here's a diagram of what it looks like. Start with the discover. With the laptop, it's looking for the server. Here's the server. Once the server acknowledges that you're there, it sends back an offer. The offer has a IP address, which is basically the pass to allow you in. It makes that request back to the server, and everything is passed through with the open pack. So that is what that process looks like from a visual diagram. And this looks like a terminal visual. The following packet capture shows the 4 steps explained above. In this example, the client gets the address 192.168.66.133. Here's just what that looks like. So here's the discover, and you can see where it does not have an address. Here's the transaction ID from a log perspective. And then you have the offer stage. It now has an assigned IP, all with the same transaction ID, and that remains the same throughout. So that's cool to see. Then you have the request stage, where it is acknowledging that it has been accepted, and then the sent back pack as listed. It's pretty cool stuff. So I like this. This is very well written out. Easy to follow and understand. Time decently spent. Let's see. In a DHCP package exchange, we can notice the following. The client starts without an IP network configuration. It only has a MAC address. Yep. In the first and third packets, the DHCP discovers and DHCP requests. The client searching for the DHCP server still has no IP network configuration and has yet to use the DHCP server offered IP address. And that is this address. Therefore, it sends packets from an IP address of all zeros to the broadcast address 255.255. Yep. As for the link layer in the first and third packets, the client sends the broadcast message not shown in the output above. The DHCP server offers an available IP address along with the network configuration in the DHCP offer. It uses the client destination's MAC address it used to propose IP address in the example above. At the end of the DHCP process, our device would have received all of the configurations needed to access the network or even the internet. In particular, we expect the DHCP server has provided us with the following: the least IP address to access the network resource, the gateway, route, or packets outside of the local address, a DHCP server to resolve domain names. More on this later. How many steps does DHCP use to provide the network configuration? That should be 4. What is the destination IP address that a client uses when it sends a DHCP discover packet? Destination IP address. I think it was using .192.168. No, I think it did too. Yep. What is the source IP address? And the answer to that is 255.255.255.255, and that is this what it was broadcasting. What is the source IP address a client uses when trying to get an IP network configuration over the DHCP? What is the source IP address a client uses when trying to get an IP network configuration over DHCP? And we see, therefore, it's going to send a packet from the IP address of quad zeros. Boom, that knocks out section 1, or task 2, excuse me. Boom, that knocks out task 2. Let's move on to task 3, ARP, bridging layer 3, addressing to layer 2, addressing. Let's do that again. ARP, bridging layer 3, addressing to layer 2, addressing. So all right, we have started the networking concept room. We stated in the networking concept room that has 2 host communications over the network. The IP packet is encapsulated within the data link framework as it travels over to layer 2. Remember, the 2 common data link layers we use are Ethernet and Wi-Fi. Ethernet is 802.3, Wi-Fi is 802.11. Whenever one host needs to communicate with another host on the same Ethernet or Wi-Fi, it must send the IP packet within a data link layer frame. Although it knows the IP address of the target host, it needs to look up the target's MAC address so no proper data link header can be created. Let's capture some notes here just so we make sure we have a good understanding of this. So what this is saying, that in the concepts room that has 2 host communications, an IP packet is encapsulated within data link frame as it travels over layer 2. Communicate over a network with an IP packet. Encapsulated within the data link frame. So it's traveling over layer 2. The 2 common data links, the 2 common data link layers we use are Ethernet and Wi-Fi. And that's your 2 ways that you'll connect to the internet. Either you're going to use a hardwired Ethernet cable, or you'll use a wireless Wi-Fi connection, or a wireless card or adapter of some sort that connects via Wi-Fi. Got it. Whenever one host needs to communicate with another on the same Ethernet or Wi-Fi, it must send an IP packet within a data link frame. Communicate. So what this is saying is to communicate with someone that is outside of the hosted Ethernet or Wi-Fi that's needing or wanting to communicate, it's going to send the IP packet within a data link frame. Itself must send the IP packet within a data link layer frame. Although it knows the IP address of the target host, it needs to look up the target's MAC address so the proper data link header can be created. Let's do that again. Although it knows the IP address of the target host, it needs to look up the target's MAC address so the proper data link header can be created. Needs to look up the target's MAC address, so the proper data link header can be created. We learned about this in the prior module, so that based upon the type of header that it is, it knows how the data needs to be sent, or based upon the MAC address, it knows what type of device it is and how to communicate with that device using the appropriate header. As you would remember, a MAC address is a 48-bit number typically represented in a hexadecimal notation, and we see 2 MAC addresses there. However, the devices on the same Ethernet network do not need to know each other's MAC addresses all the time. They only need to know each other's MAC address while communicating. So remember, we're on the same network, we're on the same team, if you will. We don't need as much clearance as we would if you weren't on our team or you existed outside of our infrastructure. Consider the scenario: you connect your device to the network, and if the network has a DHCP server, your device is automatically configured to use a specific gateway and DNS server. Consider this scenario: you connect your device to a network, and if the network has a DHCP server, your device is automatically configured to using a specific gateway or router and a DNS server. Consequently, your device knows the IP address of the DNS server to resolve any domain name. Moreover, it knows the IP address of the router when it needs to send packets over the internet. In all of this scenario, no MAC addresses are relevant. However, 2 devices on the same Ethernet cannot communicate without knowing each other's MAC address. So it has to know a little bit more about who's trying to get involved or who's trying to gain access before it's going to grant that access. And the way it's going to communicate is by the MAC address, which is kind of like, I guess, a social verification to make sure you are who you say you are. And before I do anything with you, I just need to confirm your identity. So it makes sense. As a reminder, in the screenshot below, we see an IP packet within an Ethernet frame. The Ethernet frame header contains the destination MAC, the source MAC, and the type of IPv4, which is this, in this case, is type IPv4. So let's capture that. That is IP packet within an Ethernet frame contains the following: destination MAC address. It contains the source MAC address and the type. And here's where we see that example at. Actually pretty cool. I should snippet this so I can have that IPv4 or IPv6. Destination, that's where it's going. This is who's asking, which we see listed there. And we see the destination there. And the type of connection is an IPv4. Okay. So just to kind of illustrate that out, packets, PACK sent. This appears to be, it starts with the type. And let's put this in something so we can distinguish it. Type, then the destination MAC, which is where we're going, and then it includes the source MAC. I probably should find a better way to store this, because this is a good visual to kind of help visualize what that actually looks like. I probably should put this in something other than a little note text file, but this will work for now. ARP, address resolution protocol. Um, makes it possible to find the MAC address of another device on the Ethernet. In this example, a host with the IP address of 192.168.66.89. So in this example, a host with this IP address. So we see the host where, or maybe it doesn't have it listed there because I don't see that host IP address anywhere. Okay, so that's the destination, but I don't see the host. So I'm not 100% sure that this packet is showing the actual host because I only see the destination. I don't see a capture here, but that's fine. It sends an ARP asking the host with the IP address of 192.168.66.1. So it's just not showing the IP addresses at all in this example. It's just showing what the packet looks like. Okay. The ARP request is sent from the MAC address of the requester to the broadcasted MAC. Else, as shown in the first packet, the ARP reply arrives shortly afterwards, and the host with the IP address responds with its MAC address saying, hey, this is my MAC, to go along with knowing your MAC. Let's do that again. The ARP request is sent from the MAC address of the requester to the broadcaster. So I'm going to get I'm broadcasting the network. You're requesting to come to my network. I'm going to get, you identify that I have a network. Then you show me your MAC address, and I'm going to capture that MAC address as shown in the first packet. The ARP reply arrives shortly afterwards, and the host with the IP address, which is me, responded with its own MAC address. All right, you showed me your card, I'll show you mine. From this point, the two hosts can exchange data, link layer frames. From this point, the two hosts can exchange data link layer frames. So once we've identified that my network exists, you're looking for it, you give me your MAC address. If I approve it, I get your MAC address, and now we can transmit data among each other. Cool. If we use TCP dump, the packets will display differently. It uses the term ARP request and ARP reply. For your information, the output is shown in the terminal below. So this is what that looks like. Oh, okay, so maybe it wasn't, this was just showing what this, and then this illustration went with this. I was gonna say, this wasn't making any sense. So let's revisit that. So we see the requester's IP should be in line 1, and that is here, 168. The host is here, the one with the network. The requester's IP is here. Got it. And then if we use the TCP dump, the packets will be displayed differently. It uses the terms ARP request and ARP reply. For your information, output is shown in the terminal below. So once you use the TCP dump to dump the TCP, here's what you get back. And you still see the requesters and the host information, and it lets you know the character length. Here we see that it is using IPv4. So it's going to be the 4 character length. If it was 6, we'll see 6. And this is saying an ARP request or ARP reply is not encapsulated within the UDP or even IP packets. It is encapsulated directly within an Ethernet frame. The following ARP replies show. So an ARP request or reply is not encapsulated within the UDP or even the IP packet. It is encapsulated directly within the Ethernet frame. So what you get back, you don't see that information. But within that resolution, you got the target address, the sender, the network you're trying to get to, the one you're coming from, the type that it's using Ethernet, and then in the reply back you don't see it. ARP is considered layer 2 because it deals with MAC addresses. Do that again. ARP is considered layer 2 because it deals with MAC addresses. Others would agree that it is part of layer 3 because it supports IP operations. What is essential to know is that ARP allows the translation from layer 3 addressing to layer 2. So at the end of the day, whether you want it on layer 2 or you consider it layer 3, just know that what takes place is the translation from layer 3 to layer 2. So that's their ways of communicating. What is the destination MAC address used in the ARP? So we know this is the sender's MAC address and this is the target. So the MAC address would be CC:5E F8 02 21 Apple 7. Now watch them wrong. Yep. It's the destination MAC address. So it must be what? Is it? That's the sender. 44 DF 65 D8 FE 6C. Request and it being sent. Let's see, I missed something somewhere here. Destination, MAC address, encapsulated ARP. Yes, this is the destination. Did I type it in wrong or something? That's CC 5E F8 0221 A7. That says the destination that I 02. Is that a 02? No, that should be a 02. No, what is the MAC address of 192.168? 168. Maybe I'm typing it in. 44. Or maybe I didn't need to put that. Let me try it like this. 65 D8 FE 6C. So maybe that's what I was doing wrong. Maybe I don't need to type that in. I just need to type in the sender, the target. So that's CC. Hold on. Yes, I'll tell you in 1 second. 6 CC 5E F8 02 21 Apple 7. Man, I must be hitting something in wrong. 5E F8 02 21 7. In an A, what is the destination MAC address used in an ARP request? It's not asking for this. Maybe it's asking for that. So what it was looking for is this. But I would have thought it was looking for, but I guess technically that's the sender. So, okay, got it. So I guess this is the standard of what it is here. Okay. Got it. So the next task is ICMP troubleshooting networks. So Internet Protocol Messages, ICMP, is mainly used for networking diagnostic and error reporting. Two popular commands rely on ICMP. and they are instrumental in network troubleshooting and network security. So let's go ICMP, Internet Control Message Protocol. Again, I love the standardizations and how everything has a protocol so we can all be on the same page and all have a standardized networking process to follow. In 1 second, need to bounce in and check a couple quick things really quick, and we'll get right back to it. Got any questions, let me know. Would love to answer any that you may have, and I appreciate your time and attention and you stopping by. It is greatly appreciated. Awesome. That looks good too. All right, so let's get busy with this module now. All right, so the two types are a ping, which is, it uses ICMP to test connectivity to a target system and measure the round trip time. In other words, it can be used to learn the target is alive and that it relies, and its reply can reach our system. So let's do that again. A ping, it uses ICMP to test connectivity, to test the connectivity to a target system and measure the round trip time. Measure the round trip time. So in other words, it's used to learn that the target is alive and that its reply can reach our system. So basically this is just saying to make sure that the ping is the first step, or the ping is the step, that uses the IMCP to test the connectivity target to a target system and measure the round trip time. Want to know how long it takes to get from one location to another. And it basically is used to learn the target is alive, to know that, hey, where we're trying to go actually exists and it can reach our system. Then you have a trace route. This command is called trace route on Linux and Unix-like systems, and trace RT on Windows. It uses IMCP to discover the route from your host to the target. So it discovers the route. Trace route on Linux, and I'm looking forward to using one of my old computers to set up Linux. If anyone has any experience on it, I would love to pick your brain about a few things. I know there's quite a few tutorials on YouTube, and I'm pretty sure I'll be leveraging them to help me with it, but nothing like having a go-to resource in the event assistance is needed. And I'm sure it will be at some point, if not with the installation, with some step in the process, or at least with using it. All right, so cool. Those are the two. All right, ping. You may have never played ping pong table tennis before. However, thanks to IMCP, you can now play it with the computer. The ping command sends an ICMP echo request Type 8, the screenshot below shows the ICMP message within the IP packet. So the internet protocol message, type 8 is a ping request, and I'm assuming these will represent the identifiers, the sequence number, and the response time. The computer, I assume, I could be wrong, the computer on the receiving end responds with the IMCP echo reply type 0. So type 8 is the sending of the ping request, and type 0 is the response back from said request. Many things might prevent us from getting a reply, in addition to the possibility of the target system being offline or shut down. So that's why I said if the target actually exists. Because in some instances, or if it's alive is the correct terminology used, because if it's not alive, then we know that that's not a good request and we wouldn't be able to complete that cycle. Many things prevent us from getting a reply, in addition to the possibility of the target system being offline or shut down. A firewall along the path might block the necessary packets from a ping to work. In the example below, we use -C to tell the ping command to stop after sending 4 packets. The output shows no packet loss. Moreover, it calculates the minimum, average, and maximum and standard deviation of the round trip. Okay, so that represents all of those numbers. So here's the response back. Here's the minimum, the average, the max, and the median response time back. That's pretty cool that you get a good breakdown of that. Hey, what's going on, my friend? How you doing, my brother? Thank you so much for stopping by, man. Got any questions, man? Feel free to ask away, my brother. But thank you for stopping by. It means a lot. Not bad at all. Not bad at all. Where you stopping in from? You don't mind me being nosy? Oh, learning cybersecurity. Using TryHackMe.com as my resource. I'm doing their paid curriculum plan, or whatever you call it. So right now, this is going over networking essentials, I think it's called. Yeah, networking essentials. I'm at that point in the learning path on TryHackMe. So just going over that. Let's see. All right, TryHackMe. Yeah, man. Where you stopping by from? If I could be nosy. And then you have a trace route, how we can make every router between our system and target system reveal itself. The Internet Protocol has a field call time to live, TTL, that indicates the maximum number of routers a packet can travel through before it is dropped. Internet Protocol has a field call time to live that indicates the maximum number of routers a packet can travel through before it's dropped. Decrements the packet TTL by 1 before it sends it across. When the TTL reaches 0, the router drops the packet and sends an ICMP time exceeded message. Type 11, in the context, time measured in the number of routers, not seconds. So basically, you have a certain amount of time to respond back. If that time to live, TTL, drops or the time is reached, then it sends back a time exceed message, type 11. In the context, time is measured in the number of routers, not in seconds. So it lets us know how many routers it can actually access before it is deemed no longer living, if you will. So trace route, field called time to live. That's pretty straightforward. I like that. I like that term. There's no mixing of the words with that one. Indicates the maximum number of routers a packet can travel through before it drops. The router decrements the packet's TTL by 1 before it sends it across. So it decrements by 1 every time it bounces or it leaves one router and goes to another, almost like, hey, you're losing $1 every time you change women, if you will. But anyway, when the TTL reaches 0, the router drops the packet and sends an ICMP message. When it reaches 0, the router drops the packet and sends an ICMP time exceeded message type 11. Okay. The terminal output below shows the result of running a trace route to discover the routers between our system and example.com. Some routers don't respond. In other words, they drop packets without sending any ICMP messages. Routers that belong to our ISP might respond, revealing their private address. Moreover, some routers respond and show the public IP address, and this would let us look up their domain name and discover the geographical location. Finally, there is always the possibility that an ICMP time exceed message gets blocked and never reaches us. So here, this is the request, the trace route being sent to example.com, letting us know the address, the maximum hops, and the size of the packets that's being sent. And each of these represent each stop along the way. In some instances, the IP address and time isn't displayed because it may be on a different ISP or it may be blocked for some reason, so we wouldn't be able to see it. And the other thing I wanted to see was it was decrementing. Okay. The traverse route might change as we return the command. So using the example images above, how many bytes were sent in the echo ping request? It looks like 60. So let's go with it. No, how many? The data field used to indicate the size of the request. Data field, the size of the request. 60 byte packets. Let's see. It's using 60 byte packets. Using the example of how many bytes was sent in the echo ping request. That's trace route. Here's the ping request. 56. Let's see. The other one was what, 84 that was inside of it? Oh man, hold on. ping request. I must be looking at the wrong thing. Ping, that was 98. 98. Well, it said in the echo ping request, sample images above, how many bytes were sent in the echo ping request? This is the ping, 98 bytes on wire 98. Type 8, that's just the way it's being sent. That is the ping request. And then 40 data. So that was a good learn for me. So inside of this packet request, it specifies, obviously it's a type 8, that's the ping request, has all of the identifier information. And then inside of the data, this is where the bytes live, not where I was looking previously. So I needed to make sure I looked in the right type, which was my overlook. And then inside of it, it showed the actual packets of data that was being sent, the size of it. So got it. Which IP header field does the traceroute command require to become 0? Which IP header field does traceroute command require to become 0? Which IP header field does traceroute command require to become 0? Traceroute header field. There's traceroute. IP header field does traceroute command require to become 0? IP header field required. Is that time to live? Field does the traceroute command required to become so correct. So it needs to become 0, and the time to live has to become 0 in order for that message to appear. Got it. Next, let's jump to task 5, which is routing. Consider the network diagram shown below. It only has 3 networks. However, how can the internet figure out how to deliver a packet from network 1 to network 2 to network 3? Although this is an overly simplified diagram, we need some algorithm to figure out how to connect network 1 to network 2 and to network 3 and vice versa. Here's just a diagram of what that looks like. Here's the internet, and every home and ISP would be some form of a network. This is just a slimmed down version of it. So let's consider a more detailed diagram. The internet would be millions of routers and billions of devices. The network below is a tiny subset of the internet. The mobile user can reach the web server. However, for this to happen, each router across the path needs to send the packets via the appropriate link. Obviously, there is more than one path, i.e. route, connected to the mobile user and the web server. We need a routing algorithm for the router to figure out which link to use. So here's the server, here are the routers, and I'm assuming, without have read it yet, the algorithm will be in place to identify the most efficient route to deliver the information to and from the server for the user. It would leverage the routers and an algorithm to get that done. Let's see. The routing algorithms are beyond the scope of this room. Yep. However, we will briefly describe a few routing protocols so that you could become familiar with their names. So these are the different types of routing algorithms. Let's capture those. Routing algorithms. The first one is OSPF, open, and this short is path first. Makes sense. It's the most efficient route. Everything we read so far wants to operate under the shortest path of whatever it is that we're looking for. That allows, so OSPF is a routing protocol that allows routers to share information among the network topology and calculate the most efficient paths for data transmission. It does this by having routers exchange updates about the state of their connected links and networks. This way, each router has a complete map of the network and can determine the best route. So in short words, this is calculate the most efficient paths for data transmission. Then we have EIGRP. This is Enhanced Interior Gateway Routing Protocol. This is a Cisco proprietary routing protocol that combines aspects of different routing algorithms. It allows routers to share information about the networks they can reach and the cost, bandwidth, or delay associated with those routes. Routers then use this information to choose the most efficient path for data transmission. So this is a Cisco proprietary route. So let's capture that. Cisco is a giant, so it doesn't surprise me that they would have a proprietary routing for those that want to pay for it for, I would assume, unique cases. It doesn't just want to use the open source. It would want to use something provided specifically by the provider itself so that it can get special proprietary treatment. Uses different routing protocols that combines aspects of different routing algorithms. Cost associated. Okay. The next one is BGP, which is Border Gateway Protocol. BGP is the primary routing protocol used on the internet. Primary routing protocol use. It allows different networks like those of ISPs to exchange routing information and establish paths for data to travel between networks. BGP helps ensure data can be routed efficiently across the internet, even when traveling multiple networks. So this is probably the one that's used the most, and certainly the most frequently, and used with the most networks, if you will. So we'll just capture allows different networks to exchange routing information. And then finally we have RIP, which is Routing Information Protocol. RIP is a simple routing protocol used in small networks. Simple protocol used in small networks. Routers running RIP share information about the networks they can reach and the number of hops which are routers required to get there. As a result, each router builds a routing table based on the information, choosing the routes with the fewest hops to reach the destination. Perfect. Which routing protocol discussed in this task is a Cisco proprietary protocol. We know that that is EGRP. Let's type that in. EIGRP, excuse me, EIGRP. Cool. Task 6 is NAT. Let's get ready to do NAT. So with NAT, get some notes going here. As discussed in the networking concepts room, we calculated the IPv4 can support a maximum of 4 billion devices. Yep. With the increase in number of devices connected to the internet, from computers and smartphones to security cameras, washing machines, refrigerators, yep, IPv4 address space would be depleted quickly. One solution to the address depletion is NAT, network address transition. Network address translation, not position, translation. The idea behind NAT lies in using one public address to provide internet across many private IP addresses. In other words, if you are connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. Yep. Technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. So basically, a provider can grab an IP address and provide internet access to devices on its network only using one public IP address versus each individual device requesting its own IP address. Unlike routing, which is the natural way to route packets to a destination host, routers that support NAT must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network address between internet and external networks. Generally, the internet network would use a private IP address while the external network would use a public. So unlike routing, which is a natural way to route packets to a destination host, routers that use NAT, network address translation, supporting routers maintain a table translating network address between internal and external networks. Generally, the internal network would use a private IP address range while external would use a public IP. So if it's private and it's on our network, it's going to use a private network. And if it's not within our private network, it would use an external network to gain a public IP address. Makes total sense. In the diagram below, multiple devices across the internet via a router that supports NAT. The router maintains a table that maps the internal IP address and port number with the external IP address and port number. For instance, the laptop established a connection with some web server. From a laptop perspective, the connection is initiated from its IP address. So it's going to start with its IP address from a TCP source port number of 15401. However, the web server will see this same connection as being established from 212.345 and TCP port number 19273 as shown in the translation table. The router does this address translation seamlessly. So here's what that diagram looks like, but I want to go back over that one more time because it said a lot. In the diagram below, multiple devices access the internet via the router that supports NAT. So this is the router and it supports NAT, which is a network address translation. Ooh, if I could read. Network address translation. The router maintains a table that maps the internal IP addresses and port numbers. So it has a table that says, hey, these are the internal IP addresses that we have, and we're identifying and storing them within this table, and the port number with this external IP address and port number. And here's the corresponding external network number that goes with each of those IP addresses. From a laptop perspective, the connection is initiated from its IP address 192.168.0.192, and that is right here, from the TCP source port of 15401. So it has a, and I know it didn't show it, but it has a TCP port number that's listed here. That's the port that it's going to use to gain access to the internet. However, the web server will see the same connection as being established from 212.3.4.5. So all the internet is seeing is that, hey, this is the address coming from this router. I don't care who's trying to access the internet outside of that. All I see is 212.3.4.5 and the TCP port number of 19273. That's the port number that it's using to access the internet. That's all the web server is going to see. The router does this address translation seamlessly. Got it. So basically what's happening is the router is going to access the internet with this address, this IP address. So basically what's happening is this router is going to access the internet with this IP address, 212.3.4.5. It then is going to take and create its own internal network with IP addresses of starting with 192.168.0.1. And then from there, provide internet access to the table of verified users within its own private network. And each device is assigned its own IP address, and it attempts to access the internet via the port number of its device. It's going to try to have the internet go through the port using the IP address that'll flow through the port that's going to connect to this router. And this router is going to grant access to all of the IP addresses within the internal network table. Got it. In the networking diagram above, what is the public IP that the phone will appear to use when accessing the internet? So if it's a public IP, it should see the 212.3.4.5 because that's what's public. 212.3.4.5. Yep. Assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneously TCP connections can it maintain? Whew. Man, I gotta think about that one. What's the hint? Give me a hint. Give me a hint, baby. Give me a hint. Give me a hint. We are limited by the number of TCP port numbers. Oh, no, I don't need all that, bro. Oh, there we go. TCP port numbers. Oh, where did I learn about that at? Assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneous TCP connections can it maintain? The router has infinite processing power. TCP connections can it maintain? God, I remember reading about that somewhere, and I know I didn't capture it on notes. This, I'm gonna have to hit the internet there for TCP. Nope. We're gonna have to get out there because I can't remember. Let me see. Let me try. TCP IP. How many thousand simultaneous? Google. What is the question asking me? I feel like this is one of those that assuming the router has it can technically maintain approximately 65,000 simultaneous TCP connections. This limit is dictated by the 16-bit source port TCP header, which allows for a maximum of 2. Okay, and that is the 16-bit field. I'm not interested. The 16-bit field allows for 65,535 distinct ports, thus limiting the concurrency connection that can be tracked in the connection table. Got it. All right, so the answer should be 65. I remember reading that somewhere. I can't remember where I read it at, but obviously I couldn't recall it, but it's all good. Sometimes it's just good to know how to go get an answer, and that was pretty simple. So this room introduced various protocols that we constantly use directly or indirectly. We have covered ICMP, DHCP, ARP, and NAT routing. Although we use the internet daily without coming across most of the room's acronyms, these protocols are the foundation for a functional network. Yep. Click on the View Site button to access the related site. Please follow the instructions on the site to obtain the flags. We click on View Site. Give this a moment or two to load up. Catch me some good TV later on today. I don't know. I gotta figure out something I want to eat too. Let's check this out. So, help the computer check the given scenario and click the correct choice. I want to find out the DNS server and default route of a network automatically. Which protocol should I use? The DHCP, right? Yeah. Oh, okay. It just automatically does it. Got it. Want to find another's host hardware MAC address on the network. Which protocol lets me get this information? Let me see. Internet protocol. That should be sent in a packet, but it should be drawing a blank. It should be, all right. We need to get hardware's MAC address. I remember reading about that, but I think that was in a packet, and I can't remember if it was. It's not NAT. It's not. So it's got to either be ARP or ICMP. Man, ICMP. That's the message protocol. I should have took better notes on it because now I'm drawing a blank. Let me see. ICMP. What is ICMP? Network layer of device communicator network, specifically for diagnosis of error messages. So what is ARP? Watch it give me what the non-in networking. Okay, I was gonna say watch it give me the non-networking response used to map a dynamic logical IP. So this is it. So it's got to be ARP. Yep. And then we need to give 25 devices internet access. However, we only have one public IP address. What can we use? Now this is going to be NAT. network address translation. As many times as I done said it wrong, I should know it by now. And then finally, I think the last one should be internet protocol, internet control message protocol. I want to confirm that I can exchange packets with another host as if I'm playing ping pong. The internet control message protocol. So let's copy this. Let's see if we can paste this in. There we go. So check. Boom, we are all good. It is time to join networking core protocols. Hey, go us, go us, go us, go us, go us, go us. All the haters out there in the world. All right, so good, not bad at all. So today we covered quite a bit around networking concepts. Yeah, we're gonna go 30 days in a row. We'll lock in and do it. So the next room is networking core protocols. Let's go to the room. How do I get rid of this thing? There it go. So something that I like to do, so as many of you are aware, so as some of you are aware, as some of you may be aware, I am on my journey of learning cybersecurity. And anytime I learn, I don't just stick to the curriculum. I like to supplement that learning with additional practice so that I can become more immersed in the world. And more importantly, I get more experience or exposure to different concepts and things that the curriculum may just touch on. And one of the things I wanted to spend some time learning was networking fundamentals for pen testers. I don't know which branch of cybersecurity I will ultimately land in. Right now, I'm in the beginning stages of using TryHackMe.com, its learning paths to kind of get a baseline understanding. And eventually, I'll look to gain certifications and do more with it from there. But to supplement the learning that it gives in its learning modules, I decided to start doing some daily readings and reading over articles and sharing them with you that I find beneficial that can kind of help you on your journey should you decide to learn cybersecurity, or if you just want to become better with understanding that entire cyber world, how the infrastructure works, and all of the vulnerabilities and breaches and hacks that we hear about. This will give you an opportunity to kind of learn how they work, to make sure that you're protecting your own network. And if you're building websites or you're doing anything that accesses the internet, you make sure that you put your information, your customer website, your space in the world, or the cyber world, if you will, you have it secure and locked down. So one of the articles that I found very beneficial is this network basics for pen testers. Shout out to Josh Daniels for writing this. He written it or published it, I should say, a little less than about 4 months ago or so, back in October. But I'm not going to bore you by reading each individual paragraph and sentence by sentence. But what I will say that I picked up on from this article is that I love how he talked about how having the fundamentals and a basic structure of whatever it is that you're looking to learn, that you start with the fundamentals. And although you want to learn something larger, you want to make sure you have a ground level understanding of how things work. So if you're looking to become a pen tester or work in the cybersecurity world, IT and understanding networks is a big part of it. And he starts with that as a foundation of his article, number one. So it kind of sets the tone that, hey, he's going to want you to dig in deep and have a base level understanding. And he kicks things off by talking about the OSI model. So whether you like it or don't like it, and that the more I read and learn about it, I see that there's various opinions on it, just as it is with anything tech related. If a human is involved with it, there's going to be an opinion. Some people are going to like it, some people are going to agree with it, whatever. But I love the fact that he acknowledges that. And he talks about that you need to have a good understanding of the OSI model, whether you agree with it or not. It is the standard. And I'm not going to go through each level, but I love how he gives a quick couple words that kind of talks about what you're looking for at each level. So at level 7 is the application. This is going to be where you will kind of look for authentication flaws. Level 6 is the presentation. You're going to look for expired certifications, things of that sort. Then he continues on talking about level 3 being networking, talking about IP filtering, routing misconfigs, and IP spoofing, and so on with each of the levels from there. And how you want to make sure that you're familiar with it, whether it is something that you use or something you agree with or whatever your opinion is on it. It is the gold standard, and you want to be familiar with that. Then he goes in to talk about IP addresses, how you want to have a good understanding of how an IP address works in the relation of a network. He talks about IP addresses and how they play a part within the network, and how you can have either a public or a private IP address. And you can also have either a wire, it can either be through Ethernet or Wi Fi. And being able to understand how an IP address works It's going to give a pen tester the ability to know how they need to attack and view the network that they're assessing for their pen test. The MAC address, understanding the different segments, and I can't recall the name of them right now, but I'll get better with that, I promise. The different segments identify the different types of hardware that may be connected to that IP address. And if you understand the hardware, you can kind of understand where it may have vulnerabilities and how you would want to expose those based upon what you're doing, because you can identify the hardware type based upon the MAC address. It talks about the TCP and the three-way handshake, how that client server connection takes place, how it communicates among the two. You start with the client server, that is send, saying that I want to open my connection with seek X. The client server sends back a send ACK. I see you, here's my sequence, which will be Y. And then the client server has its connection going, and that is got it. Thank you for the open connection. Pleasure doing business with you. Understanding how that works and when you come across those will help you better identify where there may be opportunities within this three-way handshake or within TCP. So it's good to have an understanding of that. So if it fails, you know to either look for it to be non-responsive due to a firewall, no connection, etc. But it's good to have a understanding of the TCP and the three-way handshake. And then it talks about the common ports and protocols. And I was relieved to see that it doesn't require you to know and memorize all of the ports, but because man, that's a daunting task. But it is good to know certain ports, because that's going to help you identify what you may be working with. And the slightest of information that is available to someone that is looking to identify vulnerabilities is going to be great to them. It's almost like a detective that is working a crime scene. They may see something as simple as a cigarette or something as a used Coke bottle as a way to help identify someone that might have been at that scene. Well, understanding ports are in the exact same fashion. And then it talked about how there is a port that's commonly used with Microsoft file sharing that has had vulnerabilities in the past. So if you are if you're hacking a net, or if you're looking to expose a network and you identify this port number, then this lets you know that, hey, there may be a vulnerability with file sharing. This may be a way for me to get even deeper within the network and identify things that I can gain access to that someone may not want me to have access to. And then finally, it talks about subnetting. I haven't spent a lot of time learning a whole lot about subnetting just yet, but I could understand what he was mentioning from this paragraph, is that you want to make sure that you're working within certain parameters, because if you go outside of certain numbers, that's going to put you in a different scope, and it may not be where you need to have your focus relied in on. So having a baseline understanding of this is good, so that you know how to manage it if you were to come across this scenario in your identifying a vulnerability state. So this is a very, very good read. And this is a very good resource. And I'll be sure to link it in the description for those that might want to follow along and read, have some daily literature to help you become better and more confident as it relates to the network and cybersecurity world, if you will. So with that, I will see you in a bit.